Alright, so in this video I'm gonna be talking about another approach for few-shot learning, and we use this for the task of text classification. And our idea is that we are using hierarchical attention protonet. It's a kind of protonet that uses attention hierarchically. So I'm gonna be focusing on this paper in 2019. Most of the current effective methods for text classification tasks are based on large-scale labeled data and a great number of parameters, but when the supervised training data are few and difficult to be collected, these models are not available. In this paper, we propose a hierarchical attention prototypical networks for few-shot text classification. We designed a feature level, word level, and instance level multi-cross attention for our model to enhance the expressive ability of semantic space. We verified the effectiveness of our model on two standard benchmark few-shot text classification datasets, FEWREL and CSID, this one, and achieved a state-of-the-art performance. The visualization of hierarchical attention layer illustrates that our model can capture more important features, words, and instances separately. In addition, our attention mechanism increases support set augmentability and accelerates conversion speed in the training stage. So this is the architecture of this hierarchical attention protonet. As you see, we give it to the encoder, and then we have this word attention. We have three attentions: feature level attention, word level attention, and instance level multi-cross attention. And finally, we can do the classification task easily. So for instance encoder, each instance in support set or query set will be first represented to an input vector by transforming each word into embeddings. So considering the lightweight and speed of the model, we achieved this with just one layer of convolutional neural net. For the hierarchical attention, in order to get more important information from rare data, we adopt a hierarchical attention. Feature level attention enhances or reduces the importance of different features in each class. Word level attention highlights the important words of meaning of the instance. And instance level multi-cross attention can extract the important support instances for different query instances. These three attention mechanisms work together to improve the classification performance of our model. Protonets compute a prototype vector as the representation of each class. And this vector is the mean vector of the embedded support instances belonging to its class. We compare the distance between all prototype vectors and a target query vector, then classify this query to the nearest one. For embedding layer, we use just this embedding matrix to embed each word to a vector. Then we apply a CNN as encoding layer to get hidden annotations of each word by convolution with kernel window size is M, because this is a convolutional neural network. Then we concatenate because the word W sub t has a position embedding P sub t, so we concatenate with the position. And then we give it to the CNN, convolutional neural network. Then we aggregate to get the overall representation. Then finally we define two layers as a comprehensive function. The fundamental idea of protonet, you know that you get the average very easily because you know the proto vectors C sub I. The rest of that is standard because you can find condition on the target query, you can see the probability over the classes. And we apply a CNN-based feature attention as a class feature extractor. It depends on all instances on the support set and will dynamically change with different classes. So given a support set as the output of the instance encoder part, so this is support, we apply a max pooling layer over each instance to get a new feature. Then we use convolutional layers. Then you see that, for example, for pooling, we have different kernel size and stride because it's a convolution. So we get a new distance calculation methods. So this Q prime is the query vector. And the importance of different words to the meanings of an instance is unequal, thus it is worth pointing out which words are useful and which words are useless. Therefore, we apply an attention mechanism to get those important words and assemble them to compare a more informative instance vector S sub j. Please note that we have 3 different attentions for different purposes. Here, instance level multi-cross attention. So given a support and a query vector, they are all encoded through the instance encoder and word level attention. And the datasets of URL and CSID, which is Character Studio Intention Detector, are used. And you'll see the visualization, you can see different word attentions. For example, here, the attention. And we have 5 classes, 5 way and 5 shots. So for each class, we have 5 examples. And because you have more classes, then we expect that it has less accuracy. And it is true. Our expectation is true because we have more classes, so the chance that you get the correct one is more difficult in this high dimensional space.